Good afternoon and a very warm welcome to the day 2 of the Autocar Professional EV Forum, where we discuss the important issues related to EV offtake in India in the country's passenger vehicle segment. My name is Mahindra and I would like to give you a quick recap of the first day of this virtual event, which was held yesterday, where we discussed about the affordability of EVs and how the automotive industry can solve this perpetual challenge. Today, we have an exciting lineup of speakers to talk about how we can develop the EV ecosystem in India, not just the supply chain, but also charging infrastructure as well. To start off the day, we would begin with the first technical presentation on the topic, Sustainable Advanced Biocircular Polymers for Electric Vehicles. I would like to invite Mr. Nicolas Dufar from Arkema, France. Mr. Dufar is Global Development Team Manager for Transportation at Arkema, France. He joined the company in 2007 and has held several business development roles. He is an engineer diploma holder in chemical and process engineering from ENSIC, Nancy, France. He also has a master's degree in applied sciences in chemical engineering from École Polytechnique de Montréal, Canada, and also holds a PhD from ESPCI Paris in polymer physical chemistry. I would request the audience to send your questions in the Q&A box, and we shall take them up with Mr. Dufar after his presentation. Over to you, Mr. Dufar.
Thank you. Thank you very much for the introduction and to give me the opportunity to present here, to present our main polyamide, polyamide 11, and how it can be used in automotive industry. So first, a few words about Arkema. So Arkema, we are a specialty materials company whose activity is split in 4 main pillars, and we have a turnover of about 10 billion euros. Innovation in materials for a sustainable world is a key element in our strategy. And we will see that polyamide 11 is a perfect fit for such innovations. It is durable, it is bio-based, it is more and more recycled, and we care a lot about corporate and social responsibility. This slide is showing the supply chain of our main polyamide, polyamide 11, which is sold under the trademark Wilson. So the raw material is castor oil. Castor plant is a virtuous crop, which does not compete with food, which grows on marginal soil, which doesn't induce deforestation. And most of the castor oil is coming from India in Gujarat. The benefit of using a bio-based product can be seen on its life cycle analysis. The difference between polyamide 11 and other polyamides is due to the biogenic carbon. Basically, compared to other polyamide, we divide by 2 the carbon footprint. While Arkema and other polymer manufacturers will work to reduce the CO2 emission linked to the process, the difference of emission between polyamide 11 and other polyamide will always be there. In other words, in other figures, so using 1 ton of polyamide 11 instead of 1 ton of another polyamide is equivalent of a saving of the emission of a car during a full year. What is also key is how the life cycle analysis is calculated, as it can have a huge impact on the final result. That is why we take great care of it, and we get audited and certified on our calculation. The value that we provide to our customer and that we provide is what we name a cradle to gate, meaning that we start from the raw material, all the steps needed to go up to the gate of our plant. After, this figure can be used by our customers then to add what will be the processing, what will be the other step, and what will be the impact on the CO2 emission. But on our side, and it is what is done by all the chemical companies, is to provide the figures up to the gate of the plant, and then after, this can be consolidated with downstream figures. Regarding castor crop, Arkema is involved in a program named Pragati, aiming at making this crop even more sustainable. In this initiative, we are partnering with BASF, Giant Agro Organics, and Solidaridad, an NGO. It is about helping more sustainable agricultural practices to increase yield and to help healthier and safer working conditions. So this is something which is not done at the level of all the plant maker, but with a growing number, and every year we have more farmers being involved in this program. Now let's have a word about supply chain, and especially about production capacity. So historically, our monomer plant, so the monomer, the base product to make the polymer, is in France, in Marseille. And then we have different manufacturing locations. We have in France, we have in China, we have in the US. And Arkema is having a major investment to increase by 50% its capacity, both of monomer and polymer, in Singapore. This is a major investment for Arkema. We are talking about €500 million investment, and this will increase the capacity, and this will also completely secure the supply chain by having a completely independent production capacity from the raw material to the end product. Now, in the next part of the presentation, we will see more in detail how polyamide 11 can be used in new vehicles. Let's first have a glance at other Arkema products than polyamide 11, which can be used for battery. One of the key products which is being used is PVDF, a fluorinated polymer produced by Arkema, which is extensively used inside the cell. It is used as a binder for the electrodes and for the separator coating. We are also providing carbon nanotubes, which are used for their outstanding electrical conductivity. And we are also developing and selling some foreign for some new, to help to develop some new electrolyte system. We are also present in the battery module and pack assembly, so outside the cell. We have some products such as Piezotech, which are piezoelectric polymers, which help to make sensors. We have also some adhesives, so with Bostik, which can be used to help make bonding of many parts in electrical vehicles. We have also some thermoplastic composite sold under the trademark Helium. And we also provide some PEKK, which is a very high performance part, which can be thermoformed, so which can be used also in the battery casing. And then in the battery management and thermal management, so on top of the polyamide that we'll see late in the next slides, we have also Bostik adhesives. We are also making some product to help to develop some new dielectric fluid in the full immersion batteries. So we can see that we have product which can be used at many steps in the production of battery electrical vehicles. Let's start talking about the vehicles which still have an internal combustion engine, but also have an electrical motor, so mainly the hybrid vehicle, and with a focus on the plug-in hybrid electrical vehicle, and to see what polyamide 11 can bring to these new cars. So among the electrified vehicles, the hybrid ones have known a huge development over the past years. In the plug-in version, so the internal combustion engine may not be used for very long distance. As a regularly plugged car can allow use of the e-motor during many days, so to work only on the e-motor, then in this case, we can have some component of the fuel system which can be extracted into the fuel. And this can lead to major issue. After several weeks or months without use of this system, if we turn on the engine, we could have some issues such as clogging of the injector. Then some OEMs are requesting some new materials which will not have components which can be extracted into the fuel. And this is the case of polyamide 11. Compared to polyamide 12, which has a high amount of oligomer, which can be extracted into the fuel. And then some OEMs are banning polyamide 12 in contact with fuel, whereas polyamide 11 is more and more used for this car with a need of low washout system. We will now discuss about application of polyamide 11 for battery management. So our polyamide, we saw a similar slide previously, are used to make battery cooling lines and the coating on the bus bar. This is the two applications that we are going to show on the next slide. So regarding battery cooling lines, so we are proposing several products to make battery cooling lines. So they are extensively used at many OEMs. So electrical vehicles, they have more and more powerful batteries. And then this increase of energy storage and release is inducing high heating of the battery. But batteries cannot withstand high temperature. Then, because if the temperature is increasing, they will lose efficiency, and they could even go into thermal runaway. That is why the cooling is a key element in the batteries. And then for the cooling, what is the most efficient is to use a fluid. The past technology of batteries were using either passive cooling or air cooling with a fan. But now what is used for all the powerful batteries which are being used is a cooling with a mixture mainly of water and glycol. And then we need to provide system to carry this coolant. And then polyamide 11 is being used for many cars to make such lines. It can withstand thousands of hours of use without losing mechanical resistance. It helps also to avoid to have two products being extracted into the coolant, which could clog some valves or parts. So this has a long time track record. So this is an application which is developing very quickly and very strongly. On top of thermal management, polyamide 11 is also used for electrical management. Bus bars, which are basically some rigid cables to connect electrodes together, they need to be coated to ensure electrical insulation. And the coating can be made either by powder process, by cross-head extrusion, or injection. And we are offering polyamide 11 to be used for all of these processes. It ensures a good adhesion with copper or aluminum, and then with an ability to allow extreme bending of the coating after it covers the part, and without removal of the coating, without cracking of the coating, without wave, and then with constant quality. So we can then extrude the line continuously and bend them afterwards. And it also provides very stable electrical properties because of low moisture pickup and high thermal resistance. Let's end this discussion on application by an emerging one, but with huge expectation. They are the fuel cell electrical vehicles using hydrogen. Hydrogen has been discussed for many years, but it has been only a few years that really started to become a reality. Polyamide 11 has been used for almost 10 years to carry high pressure hydrogen at -40 degrees and is in some high pressure line in hydrogen station. It has been used because of its very low permeability toward hydrogen, because that it has very high performance down to -60 degrees C. There is a low risk of blistering. If we have a sudden change of pressure, there will be no blistering of the material. And it can be processed by many ways on top of lines to make liner of hydrogen tanks. It can be used for rotomolding, by blow molding, by injection, extrusion. And this is, we said for almost 10 years, it has been used to make hydrogen lines. And now it's on the road to make hydrogen vehicles with where the hydrogen tank is using a polyamide 11 yarn liner. And let's conclude our presentation by the last pillar of our sustainability offer, which is a recycling. Agiplast, the global leader in the recycling of high-performance polymers, is now part of Arkema. And our joint effort, by combining Agiplast expertise on making product with constant quality using recycled polymers and Arkema compounding know-how. So this joint expertise is allowing us to develop a new range of recycled products with quality matching the need of the automotive industries, including for safety parts. We are working to collect polyamide from material producers to companies making polymer processing, such as customers, and also post-consumer, really end-of-life parts. These products can be valued. So instead of having to pay to destroy them, they can be valorized through a new life. Currently, the most difficult point, it is to collect the end-of-life parts. For example, in automotive industry, there is not necessarily a system, a place to gather the end-of-life piping system. But it's something that we are working on with some OEMs, and we are very interested to work more on it. So if you have some scraps you want to valorize, or if you are interested to launch program on end-of-life recycling, do not hesitate to contact us. So we have seen in these few slides that polyamide 11 is not a new product. It started to be sold in 1947, so it has been used for almost 75 years. And it has always helped the development of new technologies. And the electrification is not an exception. So the electrification is bringing new needs, and then polyamide 11 can help to answer some of them. Its performance and its sustainability are more than ever of great help for the automotive industries. So should you wish to know more about it or to collaborate with us, do not hesitate to contact us. We will be more than happy. Thank you for your attention.
Thank you very much, Nicholas, for that presentation. So quick ones, I would want to ask you a few questions, and we are also getting questions from the audience here in the Q&A box. So could you just briefly give us a little bit more details about the applications of PA11 that you've mentioned in your presentation?
Mm-hmm. So polyamide 11, when it has been developed for the first time just after World War II, it was used initially for textile. Then it has been used for automotive, and now automotive is a major application. So most of the polyamide 11 is being used for automotive. And it started to be used for automotive in 1955 on the DS by Citroën, where many parts using polyamide 11. And then now it's used a lot for the oil and gas industries, for the sport industries, with many shoes using shoe sole with polyamide 11. So now it's really diversified application, but with a very strong experience and strong use in the automotive and truck industry.
Okay. And are we also seeing the application of this material in the Indian market specifically? Because, here we are already seeing a lot of acceleration in adoption of EVs. So what's the trend like? Are we seeing the adoption of this material in India as well?
Yeah, absolutely. India is an important country for us. It's a growing country for us. We are having a lot of projects in India. It's a product where the raw material is coming from India. So definitely there is a lot of opportunities for electrical vehicles, for standard vehicles also. And also, so hydrogen, we know that hydrogen, there are some strong government incentive in India to go in hydrogen, and this is also bringing some very strong opportunities.
So, but are you also seeing the possibility of localizing this material in the country, or is it still being imported at this moment?
Currently, it's being imported, but we are having thought, and so now it's too late, but definitely we are open to many options, and this.
Okay.
This is being considered. Mm-hmm.
Sure. Nicholas, one last question, from the audience. So Mr. Sairam, he wants to understand what is the highest temperature that PA11 can handle to meet fire retardancy?
So in terms of temperature, so it depends about the duration, but basically in air, so the melting point of the product is at 190 degrees C. At peak temperature, it can go up to 180. And over a long time, we have some grades which can withstand 4,000 hours at 150 degrees C. So it can withstand really high temperature and even for long duration. Typically, we have some product which can be used continuous at 150.
Sure. So with that, I would like to let you go, Nicholas. Thank you very much for this presentation. And just one request from my side would be if you could just share your email ID with our audience in the chat box, in the Q&A box, so that people could connect with you. And maybe later on, if you'd want to share your presentation as well, or you'd want to connect with people. So I think if you could just do that. And a pleasure having you here with us. Thank you so much.
Thank you very much. Bye-bye.
Yeah. And with that, we would now move to the panel discussion. And I would now like to hand it over to Hormazd for moderation of the session. Hormazd, over to you.
Thank you, Mayank. Welcome to the first panel discussion of the day, which is on developing the Indian ecosystem for EVs and electrification. It's clear India has to choose its own path, taking into account market requirements, the supply chain, charging infrastructure, regulation, and of course, costs, which is super important in a cost-sensitive market like India. So to discuss all this, we have a very esteemed panel, which I would like to introduce. We have Mr. Velusamy, who's the President of Automotive Technology and Product Development of Mahindra & Mahindra. He is also on the Group Executive Board. From the supplier side, we have Vikram Singh, the Managing Director and Group CEO of Sona Comstar. Talking about the charging infrastructure, we have Anant Nahata, the Managing Director of Exicom. And on the material side, joining us is Dhanendra Nagwanshi, the Global Electric Lead of SABIC. Gentlemen, thank you all for joining us. Appreciate you giving us the time. I would like to start with Mr. Velusamy, who's actually my guru, I have to say this, and a great teacher for all things technical. Velusamy, to kick off the discussion, I just wanted your view on, on an India-specific approach to developing EVs. Do ICE platforms make sense from a cost perspective to start with? Things like battery size, vis-a-vis range. I think everything is so focused around the cost, the specs of the EV, etc. So just your thoughts. We've seen what you've done, the exciting work that is happening in Mahindra, especially, the born electric platforms. But clearly, the Indianness is what kind of defines what you've been doing. And I just wanted you to kick off this discussion with this.
Thank you calling me for this discussion, Hormazd. You are always inspiring, you and your team, as always. We learned a lot from your reviews. So coming to your question about Indianness of EVs, there are 3-4 things that one need to address for the Indianness. While range is important, the cost of EVs are dictated by the batteries, and therefore, in the transition, there are 2 goals that we need to keep in mind. In the transition phase, do we keep about 40 kilowatt hour and then about 450 kilometers range in the MIDC part 1? I refer always to part 1 because that's what famous in India. Take an ICE vehicle and move forward, but there are compromises to that, and then the multiple compromises to that. Second is, in the long run, we will survive only in India MIDC part 1 cycle if it is 650 and above, which is about anything between 75 kilowatt hour to 82 kilowatt hour. That's the 600 kilometers you need to give for the customers. And how do we make that affordable are the 2 questions. Whether can OEM make it and make it affordable. So these are the 2 broader goals. And how does the approach take place? In a transition era where you are 30 kilowatt hour to 40 kilowatt hour and you're taking an ICE vehicle, of course you have challenges of ground clearance, challenges of turning circle radius, dynamics, and so on and so forth. For example, your AC system is inside your IP, you don't have a frunk volume, you don't have a lot to play around with the dynamics of the vehicle, your high-speed performance is limited. Are you be comfortable at 160, 170 kilometer per hour on a Mumbai to Nagpur highway? One thing is the power wouldn't allow you. Another is even if the power allows you, an ICE converted vehicle will have limitations, its own limitations. The brake system, the steering system, the suspension system, all of them will have limitations. We can go into the details. So clearly, in a transition to declared value of 450 and real value of maybe 300 kilometers. Somebody might pull me for this statement, but you hear from the real world. About 300 kilometers in a transition for a city drive of an EV to start with electrification, ICE derived one, but clearly the final goal of 650 MIDC part 1 is upon electric. And as we go into the discussions, I will reveal more about what's the difference between PON electric and ICE vehicles, Hormazd. That's my input.
No, thanks very much, Velusamy, for those opening remarks. But a couple of things. I just want to press you on one thing just to before I go to Mr. Singh and. Fundamentally, you've talked about the product side. I just wanted your thoughts a little bit on the supply chain, because clearly this is one big challenge. The cells that's one thing you cannot get from here, but there's other components as well. From what I understand, even for you, the motors are still being imported. We will hear from Mr. Singh of Sona, Comstar, what they're doing on that front. But Velusamy, just to understand, from the supply chain, where do you expect the supply industry to really focus first on what critical components should they be focusing on localization to just make let's say the cost targets also viable?
So there are, let's start with the battery. There are multiple stages in the battery. So you buy a cell and you make a lean model or a compact model, and then you convert the battery pack, and the battery pack goes into the vehicle. So someone can do the frame of the battery, that's a localization possibility. Someone can do the model for the OEM and integrate that into battery pack. So that's the two steps that drastically reduces the cost. So inside the battery pack, you have cell, you have CSC, the cell supervisory circuit that you have, then the PDU, the battery distribution unit for the allowing the flow of current from the battery to charger to outside, from outside to inside, AC, DC, both ways. And then you are giving the power to the water pump and the e-motor. Basically, e-motor, you are giving the power. Now, these PDUs you can localize. Then you have a BMS, the battery management system, that is monitoring the voltage, current, and temperatures, and then guiding the whole system and its software. So the BMS, the PDU, the cell supervisory circuit, and the frame, the module. For example, if you take some X value of kilowatt hour of the cell, you add another close to 30% you add to convert, when you add all these components to convert into a battery pack. Now, clearly all these components can be localized, leaving alone the cell. So that's the one point. Second, coming to charger, the charger has the two-way chargers.
Right.
And that can be localized. Clearly, that should be localized. We have enough volume now coming up, should be localized. Motor, transmission unit, motor control, MCU, that needs to be localized. There are apprehensions about the motor core coil that's being still imported, but we need to push as an industry to localize the motor control unit and the transmission unit. Transmission unit by far will be to start with, you assemble all three, but then localize the transmission, localize the motor components, housing and stuffs, and then localize the motor control unit. So charger, motor, and battery, these are three components that we have discussed about it. And the rest are vehicle electronics. A lot of stuffs around vehicle electronics, and as we go about, we will talk. To safeguard these, you put a lot of hot stamped materials, and hot stamped materials today everybody is localizing. So I don't worry about the vehicle side of the hot stamp. The hatchback system that is there for the battery and the hatchback system for the cabin, they are integrated in the battery electric vehicle. Those components need to be localized. Electric water pump, electric vacuum pump, and the radiator and the condenser, all of them have to be localized. So that's a big area, chunk of area that can be localized.
Right. No, thanks. Really, thanks for that overview. I think what's clear is we all know the challenges of localizing the cell. That really is the secret sauce, but requires a huge amount of investment, and we get to see that. But after hearing Velusamy, there are so many other components that we have the scale to localize, and it's still not happening. Mr. Singh, I'd like to turn to you because you've been looking at e-motors. You've been doing this, and this is specifically for the passenger car industry. Just wanted your reaction to what Mr. Velusamy has been saying on the scope of localization that needs to be done. Clearly, the supply chain is not developed at all. I think that is one of the challenges. But I want to understand, how is it transforming, and how do you see the kind of supply chain developing in India?
So thanks so much. Velusamy has said the right thing. It isn't that complex. To be honest, if it's low voltage systems, it is actually not complicated at all. We pretty much have the entire supply chain. So first is battery to motor. I won't get into that because I'm not an expert, but motor to wheel is basically motors, controllers, and transmissions. I don't know if you know, but we are, as Sona Comstar, already perhaps one of the largest in the world in the gearbox space. We have about 15% of the world market share when it comes to EV. Motors, we started at a lower scale, I think at the lower voltage systems, and that's the challenge. And I think if you separate out this problem, but what Velusamy said, 30 kilowatt, 50 kilowatt, that's actually eminently solvable. It gets tougher as you go to higher voltages. Because, there are 4 areas you need capability as well as knowledge and NPD iterations many times to actually get a product that can be given readily. So high voltage systems engineering. Second would be functional safety. Third, thermal management. And this is where actually there is some weakness. And fourth, materials. I will just put in a broader category. And there are many material problems that we have. High-grade steel laminations we don't have. Rare earth magnets we don't have. So there are issues in also developing it fully locally, even for us. Now, there are 2 ways to go about doing it. There are partnerships that you could go do with global technology players via JVs or licensing agreements with startups, because for almost everyone, this is a new field. So if you are experimenting with an EMSM motor or an SRM motor where you've solved torque ripple, it isn't something that has been done before. So it is new for those voltages. You can also choose the independent path, the slow one of developing it indigenously, which is slow but organic, but gets you there. I think for motor and gearbox, which is our core domain, the localization potential is very, very high. I would say if we can solve, and which is what we're looking to solve, the magnetless motor stuff, up to 100%, barring the magnet part. The other parts where there's challenges still exist, and Velusamy said it rightly, the power electronics and software. Even for us as a company, we need to develop more capabilities in design, testing, and integration. We've made a start. We have about 50 software engineers now full time, but it has taken us a while to get there. And I think there is a long road to still journey on. I think there is a way to get it done that OEMs can start with a build to print approach. There's no shame in not being the first to design in that, and then look at complete localization after a couple of iterations. This also offers all tier ones like us, good enough time to engineer, test, and launch, because these are safety critical components. I don't want to belabor that point, that people have rushed into this, and fools rush in where angels spare to tread. And that has led to some, at least in the two-wheeler space, some apprehensions which could have been avoided. 1 more year could have been taken. So yeah, I think the potential is fairly high.
Right. I think you raised a point also on the safety issue. I think clearly, given this nascent stage, I think a lot of learnings still have to come in, and unfortunately, that's resulted in some safety issues. As you've said, I want to come to that in a bit, but I think I'd like to get Mr. Nahata in because I think clearly Velusamy said that localization of chargers is possible. We have the scale. So, Mr. Nahata, I just wanted your view. The the current, let's say, landscape of charging? I mean, the sense I get is all 25, 50, 60 kilowatt hour. Is that enough? Will we need more? How much more penetration do we need to kind of build the ecosystem to a point where, range doesn't become so much of an issue, and that clearly in a way would benefit OEMs because they don't have to push for bigger batteries and more range. And, clearly there are still issues with charging infrastructure. I mean, a lot to be done. And we had one panelist also who's given a question that a lot of them are not even reliable. They don't even, a lot of them don't even work. I know these are early days, but how do you see this panning out and, let's say the kind of penetration going forward?
Right. So thank you for having me as part of this panel. So we have, as Exicom, we have been working in the charging infrastructure space for about 3 years now. And we have come a long way. Basically, if I remember 3 years ago, it was a catch-22 situation. How will EV come? That there's no charging infrastructure. Why will charging infrastructure come? There are no EVs. And early days, government solved that problem by coming out with significant large tenders at those times, which kick-started the charging infrastructure deployment in India. From that point to now, we have come a long way where I think roughly even as what we call as destination chargers, which are not in people's residencies, almost 500 fast chargers would be getting installed on a monthly basis in India, which is not a small number. Does that solve all the challenges? No. Does it cover all the main regions? The answer is no, but we are moving fast towards it. Globally, the metric is one charger, one connector over 10 EV vehicles is a good good estimate of how the coverage should be. Now, this may change from country to country, city to city, depending upon how people use residential charging, but broadly that's a good estimate. I think in India today we are 1:50 or something, but because it's early days. So a lot of charging network expansion, what is happening today is for creating that network effect. It's to cover the major geographies, to provide coverage. And then, once coverage is provided, we'll later see, charging infrastructure getting more deep, which is to cater to the density of the electric vehicles. On the localization part, in fact, we are, our history of our company is to do with power conversion, which is a very similar technology what is used in charging. So since we had command over that technology, it gave us some let's say some natural push towards charging technology. Today we have AC chargers, and those are not only being supplied to the leading Indian OEMs like Mahindra and Tata, but even to Volvo, to Audi, to Hyundai, to Kia. Which kind of validates the availability and development of global technology in India. It validates the usage of it by all multinational OEMs. So we're proud to say AC chargers, not by just us, but many other companies today, is more or less fully locally designed and locally manufactured. Like any other electronic intensive industry, obviously all the components do come from outside, all the semiconductors and so on, but localization is very high. On the DC chargers, I think we still have some journey towards reaching that scale of localization. But again, taking our own company's example, except the power conversion converters, the AC-DC converters, all the electronics, controllers, the softwares, the 8 microprocessors running in a DC charger and doing a variety of things, all that is localized. As my colleagues also mentioned, it's not rocket science. We have some great, software skill set, hardware skill set. It's a question of putting that together, having a roadmap, and exercising that. So, yeah.
So before I come to you, Mr. Nagwanshi, I just wanted to get one thought from Mr. Velusamy on the charging side, which I would like Mr. Nahata to also respond to. On the DC side, we're looking at 25, 50 kilowatt and that range. Clearly for maybe the current battery size, it's okay. And for 1C charging. Velusan, I mean, what do you expect from the charging network? I mean, I'm talking about, one is obviously the network which is happening and the penetration. But do you see in the future going from 1C to 2C, in which case, the charging capacity would have to be, let's say, upped and, for faster charging, and especially when you start using EVs as long distance vehicles, because right now the proliferation seems to be up to the 50 kilowatt mark for the DC charger. Do you think there is a need to go more than that, given the way vehicles are developing, or are we fine with 1C for the moment, for time to come?
So, Hormazd, 1C will not clearly work. As we should see it, transition phase and then ultimate goal.
Right.
Customers want 80 kilowatt hour battery, and that needs about 150, 160 or 175 kilowatt motor. The 80 kilowatt hour obviously will need, if you have to charge it in 30 minutes, so 80 kilowatt hour would need 175, 160 kilowatt per hour. If you have to do it in half an hour DC charging. So that will come between 25 to 27. I expect this to mushroom everywhere because that's the period where, like in Europe, today the battery electric vehicle penetration is 12%, which is incredibly moving extremely fast, proliferating. They are in that 80 kilowatt hour battery range, and most of the demand is for the high volt charging, DC charging. That's because the 30 minutes time frame. This still will be a premium in my view, because the 4 meter segment with 30 kilowatt hour, 40 kilowatt hour will be in larger numbers. That would mean about 25 kilowatt charging to 50 kilowatt charging. So both will be there on side by side.
Right. Mr. Nahata, just hearing what Mr. Velusamy said, clearly, 1C is not going to be enough in the future. Is there a plan to kind of, do you have this time frame in mind that you will have to be going with higher capacity chargers, and also the whole issue of the grid and, let's say the infrastructure to support that? I mean, is that a challenge, or do you see it naturally progressing to that in time?
Right. So in terms of the power rating of chargers, even today we supply chargers up to 320 kilowatts, because for buses, any heavy duty vehicle, the charging is moving. It was about 180 kilowatts.
Those are mainly at the depots, I would imagine. Where
absolutely.
It is talking about from the passenger vehicle point of view. Yeah.
Agreed. So passenger vehicle today, as you rightly said, 60 kilowatt is the norm today for most of the commonly available cars. But when you see some of the cars being launched by luxury brands, Audi, Mercedes, we are supplying a lot of DC chargers to them. As rightly said by Mr. Velusamy, the charger requirement starts with 120 and even goes to 180. So in Europe today, most of the deployment, even for passenger cars, is in the range of minimum 150 and upwards even to 300 kilowatt. That is going to be the trend going forward because the cars are capable of accepting that level of charge. So people's expectation about charging times is going to go low. Grid is going to improve. They're going to be moving towards 20-minute charge, which 100% will move the market in that direction. Now, India is a lot of people say small car market, less than 4 meter car market. So there will always be a segment where 60 kilowatt chargers will also work. So I absolutely agree. There will be, both will go grow in conjunction together.
Right.
You also asked about the grid perspective. Yeah. So I think that there have been a lot of studies and a lot of articles that if everybody starts charging at the same time, the grid will fall. So while there is no disagreement that there is a lot of investment required on the grid side, but generally, even if we consider very optimistic penetration of EV cars in India, the overall grid requirement is power requirement from the capacity of the grid as a percentage perspective is not more than 7-8% of the grid. So as such, grid is not an inhibitor in terms of creating very big charging networks. Yes, there are issues when in a local community, there is a certain feeder capacity, everybody starts charging at the same time. So we have to come up with already accepted systems worldwide around the areas of smart charging, which limit the charge per car depending on time, depending on the load on the grid, etc. So with usage of those smart systems, which are not far away, at least we do not believe a grid will pose a serious challenge to penetration of electric vehicles.
Right, interesting. So I think clearly what we've heard from both Mr. Velusamy and you is that, there will be a move towards obviously faster charging. That is definitely needed. And clearly we do have the grid support to support that as well. So I think as cars get come with bigger batteries, I think that's when the tipping point is. And I think Mr. Velusamy gave a good time frame where he feels between 2025 and 27 is when we will see the sudden shift to where cars will come with bigger batteries, and as a result will require faster charging. So I just want to now change tack a bit and talk about let's say the whole safety issue, because I think with all the thermal incidents that have happened fundamentally with two-wheelers, it's on everyone's mind. And I'd like to bring in Mr. Nagwanshi, because they deal with materials, and just to understand how material technology really can come in, and especially in terms of battery safety. Mr. Nagwanshi, over to you.
Thank you, Mr. Hormazd. Good afternoon, panelists. A warm good afternoon from Detroit, the Motor City of the world. And also a warm welcome to all the attendees of this webinar. Very happy to be part of this panel where the entire value chain is present, from the car manufacturers to the charging infrastructure supplier to the tier ones. Yes, electric vehicles bring several advantages, correct? More efficient vehicles, lower CO2 emissions, and more simplification for car manufacturers, but it brings several challenges as well. Battery is a brand new component which is being added in a car. And this new component is one of the heaviest, one of the largest, and one of the most expensive component today. And it comes with a new requirement like safety. These are high voltage systems, and there are several cases where these batteries have caught fire in a recent time. So it's a challenge, and looking at this, presently steel and aluminum are the materials which are commonly used in a battery pack. These battery packs are heavy as well as complex and expensive. So to address these challenges, SABIC as a material supplier, we have been developing some very unique materials, which are flame retardant materials. So these materials, when they come in contact with the heat, they start forming a char. And that char becomes an intumescent protection layer, and that separate oxygen for to prevent the thermal runaway propagation. So the conventional systems need to be relooked, how the mica sheets are used, how the thermal insulation blankets are used, how the cell separators are used, and with these new materials, new processing technologies, and new design considerations, the battery systems can be further optimized. And in addition to all the benefits, even the safety can be improved. Plastic is not conductive, correct? So that's the first thing comes to the mind, that okay, in a high voltage system, as they use a thermoplastic material, that reduces the risk of high voltage. And if it is engineered right, the thermal propagation can be controlled either at a cell level or a module level or inside a pack level with the different strategies.
Right. Thanks for that. I mean, interesting to know that, there are fire retardant materials. I'm sure, everyone in the supply chain would be interested in that. And even Mr. Velusamy. Velusamy, I'd like to turn to you overall on safety, and specifically battery safety. Clearly, when developing the vehicle, the high ambient temperatures in India pose their own challenges, and you need to have the proper cooling. But now, do you think even the new battery norms and regulations, which are just coming into effect, December 1st, and then following a couple of months later, that overall, fires will be a thing of the past? Well, maybe not. That can, hard to say that it'll never happen, but it would be a very rare occurrence given how much we have learned already, and the fact that now we have even tougher standards coming into play for batteries.
So on the battery safety, I would like to split into three zones. The quality of the battery cell, the quality of integration, and the materials used inside. That's one part of the story. And the second part of the story is the monitoring, the BMS monitoring of the cell voltage, temperature, and which is the weakest cell that is running out of power, and that's getting stressed out and starting to thermally propagate. Ability to detect that. So that's the electronics portion, the calibration portion of it. Third is the integration of the battery pack into the vehicle against the frontal crash, against the side crash, and the whole HVAC system, cooling system, the battery cooling models. This is the third system. Obviously, there are fires that we have seen, and that's literally making sleepless nights to the EV manufacturers. And before they put the finger on the problem, it becomes very difficult to resolve. The government of India, the regulations that they are releasing now, taking the safety, is absolutely welcome, and I'm sure they will give us each OEM the required time to implement it of those vehicles which are already in production. But it is also making all other OEMs to think, and the component manufacturers to think, to make sure that globally all available regulations, we need to ensure that we meet for the upcoming vehicles. That's one thing is running in every OEM's mind, and they are doing it. So therefore, I don't think any vehicle that is coming in 2024 or 2023 might have these issues. Maybe there are issues that we have seen in the earlier vehicles. Now, you start with the cell chemistry. The LFB is more suitable in general, it's more suitable for a high temperature application because the way the cell reacts inside, LFB is more suitable. In the design of the battery pack, you tend to become cost effective when you use LFB cells when the safety measures to be introduced, because the NMC cells need much more the thermal barriers that needs to be increased, and different grades of mica sheets to be introduced, because the NMC cell, by virtue of its chemical reactions inside, is more prone at a higher C ratings of current pull out from the battery cells. It is more prone. Nevertheless, NMC cells are working in high temperature regions. I'm not ruling out. You need to spend little more money in order to do STP, so-called STP, stop thermal provocation. That is the need of the hour compared to LFP cells, and both being at same energy levels. The OEMs have taken it because it's their investment. Any one fire in a parking lot will destroy their complete brand. Right. So that's the full stop for it. The way I interact with many OEMs and component suppliers, it is on their topmost priority, and there are technologies available to stop. The one thing is that we need to purchase quality cells. That's the bottom line, quality cells, and make sure that the BMS is properly applicated and battery is properly applicated to the side crash and front crash.
Right. So obviously, I think at the cell level, it all starts there. The quality and safety starts at the cell level, from what I understand. And clearly that's, and as you said, LFP obviously has an advantage. And Velusamy, just to understand in India, what are the kind of high ambience you would package against it? Would it be around 45 degrees? That's where the testing is done, just to make sure that, thermal conditions or the thermal safety is met, because obviously our ambient really poses a lot of challenge and in peak summer.
Hormazd, you have gone to Tilsit and many videos we have seen Renuka and US and posting from there. It goes as high as 49 and 51, and there's a heavy watertight sealing of the battery pack, and then you run your cooling system there. Inside, you need to maintain that required temperature. So I would test an outside ambient of up to 60 degrees to make sure that we never have a problem with respect to battery thermal runaways. We need to test this. And that's easily possible that you have a thermal environmental chamber for the battery pack, for the module, and for the cells. And just run 1C, 2C, 3.5C, and then 2T cycle, put the complete pack in there, have the, of course you derate it. I mean, you don't allow the same currents to be drawn. Of course you derate it, but this testing needs to be done. And needs to be done at the SOP stage and not at the A sample or the B sample. We are seeing differences in the cell behaviors between A sample and B sample and the production cells, and then therefore it is utmost important that we do this testing.
Right, and that's quite interesting. You said that up to 60 degrees Celsius, that is quite a brutal test, but I think clearly you got to make sure that you're absolutely protected against any sort of one thermal incident, because as you said, it can destroy the brand. No, thanks for that. Very, very, insightful, Velusamy. And, Mr. Nahata, I just jumped to you because we've got a question from one of our viewers, Mrs. Disha Jugat. She wants to know on the charging side, are now smart chargers important considering the recent fire incidents? What can be done on the charging side also? Because clearly that's where a lot of the thermal, that's also are responsible sometimes for thermal incidents as well, just the way that happens. So just your thoughts on the safety from the charging infra side.
Sorry, my bad, I was on mute. So most of the fire incidents which have happened in India, they have happened in the two-wheeler space.
Right.
And when I talk about charging, it's a very, both the physical interface as well as the software interface of how a battery interacts with the charger is critically important to ensure safety. Right. For the four-wheelers, all the way from passenger car to buses, these interfaces have been very well defined. And that's why, globally, we still have seen incidents because of other reasons, but not so much because of interaction of charger and battery. However, in the two-wheeler space, these interfaces are not well defined. Every manufacturer follows their own choice of connector and communication with the charger. And a lot of vehicles where you have seen fires, there has been no communication with the charger, which means in technical language, the amount of current or charge you can provide to the battery is not regulated, which is unsafe. But the recent amendments by the government, has put a stop to this, and while not specifically defined the interface, but has mandated that there must be a qualified interface between the charger and the battery. So I think that will absolutely increase the safety of the battery pack. But in short, this interface is very, very critical.
Right. Do you think there is a need to standardize the interface? I don't know if that's feasible. As a further step to kind of ensure further safety, or do you think enough is being done? Because clearly, there are really tough regulations on the battery side, but I don't know whether the charging side also needs to have certain tougher standards just from the safety point of view.
Right. Absolutely. Very fair question. So, as we speak, there is already a lot of work underway in the government to standardize the interfaces. So, for example, for light electric vehicle fast charging, there has been no standard up till now. Still hasn't been published, but I think we are in the semi-final stage. For that standard to be defined, which everybody will start using, and that will have all the software interfaces defined, physical interfaces defined. So we are absolutely going in this direction. There are still some gaps, and to bring everybody as part of consensus, whether the industry and all the stakeholders does take some time, but we are on that course.
Right. And Mr. Nagwanshi, I'd just like to turn to you, sticking with safety and the fires. Clearly, you've got materials which are fire retardant. Obviously, the OEM suppliers don't want to put that to the test. It's more like an insurance. But I just wanted to get your thoughts on, the importance of regulations for product safety. Do you think enough is being done? More needs to be done? Or this is such a new technology. We are still at the beginning of a journey that we still need to understand further certain thermal incidents, why they're happening, and what can be done to prevent them.
Absolutely, more needs to be done today. The battery technologies are evolving. The battery architecture is evolving. Each car manufacturer's battery pack is different. There's no standard cells to standard modules to the standard way of assembly. And what you expect to do in a battery in a car is also different. Someone wants it as a structural member of a chassis. Someone wants it like a non-structural members. So right now there are very few harmonized regulations. Some of the GB test standards in the China, that's where it started from a bonfire test side, which are being globally adopted. But for the thermal runaway scenario, each OEM decides based on their chemistry, their architecture, what kind of testings to be performed that can work for their architecture. There's one particular test I would like to highlight. Is from the Underwriters Laboratory. It's a UL 2596 test, where it's one of the most stringent tests that simulates the thermal runaway phenomena. And during this test, 25 cylindrical cells are put on a thermal runaway, and a material which needs to be validated goes on the top of it. And then at a high pressure, high temperature, with all the ablatives going on, the performance of material is validated. So that's one such standard which is available today for a preliminary screening. But right now, it's with the car manufacturers based on their cell architectures and the chemistry, and what kind of temperature profiles they are observing, how much energy is inside each modules or inside the pack, and a right materials need to be selected, a right design need to be selected, and in combination with the right the cooling technologies, these batteries can be designed safer.
Right. Again, Velusan, coming to you. I mean, is there a case for standardizing battery packs, standardizing chemistry, or do you think that's really the secret sauce which OEMs like yourself, let's say, I would say, very brilliant engineers like yourself actually don't want standardized, because that's really what gives you the edge in terms of product. But, there is a case for standardizing certain things, to just make sure that everyone following that path has a certain safety standard, which is known. So really, I think there have been talk of standardizing a lot of things at the battery side, but just wanted your thoughts on that.
So, Hormazd, from China and US, you already have a lot of regulations. The regulations for the battery packs are coming from three directions: the aircraft regulations, application of the batteries, the land applications of the batteries, non-automotive applications of the batteries, and the tests that have been proposed by Chinese and US regulators to the OEMs, basis the initial proliferation of the electric vehicles. My journey is very limited, and in the limited journey, when I started, we used to refer the nail penetration test as the biggest test, and then and the flame test. Those are the two tests that you in a bunker you do the test and the whole battery explodes. I mean 80 kilowatt hour or 40 kilowatt hour, if you do it, the whole battery explodes. But then people started developing stop thermal propagation measures, and in the nail penetration test or the flame test, you need to pass. And then you have side crush, front crush, all these crush tests, and crash test. Both you have to pass. These are the three very big tests that you need to pass. Apart from dropping the, in a 6 meter height, you drop into the water, you drop into the, you do the thermal shock between minus 30 degrees to plus 70 degrees. In a chamber, you move up and down, you do all these tests. But the most important test is the nail penetration test.
Right.
Now, the UL underwaters name implies that underwaters for a safety test. Underwaters test brings in a lot of additional tests for the OEMs, and OEMs needs to invest, and cell manufacturers and module manufacturers have to invest on it. As we go, maybe in another couple of years, we will learn much more tests coming from automobile use, apart from the static energy storage users. There is a need to, today when I see the battery pack development cost and the test, I've never seen such a cost for an engine development. Yeah. And the number of tests, the varieties of tests, and then you need a bunker to test a battery. And each battery pack is very, very expensive. So this will force everybody to standardize and do only once and don't do multiple times. I mean, A sample, B sample, C sample, one OEM to other OEM. There will be a cell standardization, module standardization, battery pack standardization will occur. And therefore, that will limit the number of tests that one needs to do for battery pack development. It's becoming extremely expensive, battery development. When do we stop growing the number of tests, identifying the number of tests? I don't know, maybe at 3-4 years down the line. But there will be a day where after 3-4 years, there will be standardization. But as you said, some OEMs will hold the knowledge, and that's where the secret sauce lies in there.
That's right. I think the battery is the secret sauce, but I don't know whether Mr. Singh would say that even the motors have a clear role to play. There's a lot of technology development, and I'd like to get your thoughts on this. Specific to the Indian market, what sort of technologies vis-a-vis performance, obviously cost, efficiency are we seeing, and clearly looking at the way the Indian market is developing. Will we reach a point where we have enough economies of scale to become even a global EV parts hub?
So, the Indian auto comp industry, it is good at one thing. It is good at handling scale. That's the one issue we don't have. With the EV opportunity, though, there are some unique challenges in supply chain. I think I mentioned a couple of them. High voltage EMS capability. Motor component sourcing is an issue for people like us who make motors, high-grade, thin lamination, electrical steels, inverter components, IGBTs, if you want silicon carbide or gallium nitride power devices, again, it's a challenge. Building manufacturing capability for these sub-assemblies is also essential because we have our own tier 2, tier 3, and they are largely missing at this point. Getting the right technology, machine tools, testing facilities, training and retraining of associates and shop personnel, and safe handling of high voltage components. All of this is largely missing, and we are having to develop it from scratch in quite a lot of times, and it takes time. But Hormazd, the bigger question I would say, if we want to become an EV export hub, is not going to be of scale. It is going to be one of mindset. Again, not to self-aggrandize, but we are one of the very few companies to have done well as an EV parts exporter, right? To China, to Europe. And we actually started this in 2017 to the better known names in the EV world. And I think the mindset problem is the bigger one, that first, more companies have to have the self-belief, the conviction and the hunger to play on the global stage, compete, fail, because failure is inevitable first time around. Pick yourselves up again, try again till you actually get it. Because to supply to the best out there, you have to be the best at what you do. And it's not an easy road to walk. And a lot of people don't want to, right? Because what it would mean, and this is the second point, it means owning and controlling the primary technologies that you use to make your products. Yes, there'll be some outsourcing, but at least the primary things. So if you're a gear guy, gear design and metallurgy should be yours. If you're a motor guy, you can't be winding and the lamination, everything can't be outside. Then who are you? Right? If you're building a vehicle, someone actually said to me that हम तो डिब्बा ही बनाने के लिए रह गए because you get the battery pack from someone, you get the 3-in-1 EDU from someone. What would you make? And that thing that you have to iterate continuously on that product or the system with a paranoid mindset to keep making a product or system better as well as cheap. Build to print has got Indian auto industry quite far, but it is not going to help if you want to matter on the world stage and say things like EV export. And third, I think this is also our greatest strength. We need to leverage our biggest and perhaps only natural resource we have, which is of world-class quality and is abundantly available, which is our engineering talent. I mean, we have great engineers in this country. And the more value addition that we add from engineering time into the product of the system, that's our strength. Labor cost arbitrage is dying to nearly dead. I mean, if you look at productivity and do it, Mexico, China, my plants are equal on labor cost. But engineering cost, we have a 5-6x advantage. If we leverage that, yeah, we can. But again, huge mindset shift. Small car market, again, this is thinking of India as Indian suppliers to Indian market. Unless we think of, yes, we are making mostly in India, but we supply to pretty much everybody. I mean, Hormazd, if you go to North America, you sit in any electric vehicle, 9 out of 10, the probability is we'll have something in it. Right? We started there. If you do that, small cars, I think are very testing and is a great challenge for any engineering or manufacturing company because it tests you on your ability to engineer economical products that are compact, much smaller, and yet have features like safety, comfort, reliability, which everybody has to have that same standard.
Right.
So, yeah, I mean, and one thing everyone talked about standards, I want to add, I mean, it'll be great for us if people figure out what is the voltage standard everyone in India wants. Because look, people are saying 400 volt, 800 volt, 220 volt. Somebody has to, because we have come far from 48 volt to let's say 96, 120, but it cannot be completely open-ended. Also, the other standards like functional safety, which ASIL-C, B, D, whatever you choose, for make it consistent for all OEMs. ASPICE, AUTOSAR, cybersecurity protocols, OTA. These are all fairly now standard. I mean, we are not seeing very divergent views from different OEMs. That also helps tier ones develop products faster.
Right.
Yeah, sorry, just want to choose that.
Sure.
It is quite important to ensure that these standards are not watered down when we are implementing them locally, because once you lower standards for any reason, that low point becomes a new standard. So that's something we'll watch out for.
Right. Thanks for that, Vivek. But I just want to again toss this back to Mr. Velusamy and ask him a very frank question that what would it take to, let's say, source a motor locally? I mean, ideally, Sona should be supplying motors to them. Velusan, clearly, I think that's one also very expensive and critical component which can be sourced locally. I don't know what the plan is right now. From what I understand, you have some other global suppliers for this. Clearly, you would need, let's say, you would prefer an Indian supplier. What is needed for that? And again, to another point, the second question is really, I think, a pertinent question which Mr. Singh raised was on, do we need to standardize even on what voltage we want? Because there's 400, there's 800. Is 400 good enough for India? Do we really need to go to 800 volts, which is a global thing? Or will the whole supply industry also move to that, which might force us to move in certain directions? So just these 2 points, especially on, let's say, things like the motors, which are also critical components and ideally should be sourced locally.
In general, I will give a comment on the motor localization. Everyone is putting enormous effort in motor localization because there is a 21% duty on it.
Yeah.
And we know the 5% GST is to give a kickstart to the EV story and EV transition. It's not going to go and survive for a longer time. And the faster we do it, the better we survive the momentum, and then from there onwards, automatically we take on. And And to survive automatically with the increasing GST as the EV volume come, will be the localization of the motor, the 21% that you would never pay for it. Yeah. In the initial phases, you will import it, but there is a great amount of effort being put in to localize, and every best supplier, we would like to go and source it. We have enough volume to source it, and if that is Sona, they will be the source, and our sourcing team and Vinod Sagai will decide it. But every competent and quality supplier will have a space.
So Velusamy and Hormazd teams are already in touch. So we are working with. I don't name our customers usually, but we are already engaged on this.
Yeah, I would imagine that would happen in time. So, but and Velusamy, what's your view on the architecture? I mean, talking about 400 volt, 800 volt again, which Mr. Singh had raised.
So, Hormazd, in the EV, the scale is the most important thing.
Right.
I have developed many ICE engines, transmissions, and vehicles. 4 vehicles that the recent vehicle that Mahindra launched. I know we sourced it for 50,000-60,000, and right now we are in a game of nearly completing the sourcing for our EV vehicles, as we declared in 15th August. UK 60-70% was over in August, and now it's nearly most of them is over, nearing to over. I have seen the benefits of 50,000, let's say 100,000, 100,000 versus 150 and 200,000. Right. It makes the supplier to invest locally and to bring a bigger team to commit for the EVs. Yeah. Now, if you look at the segment, I know I'm giving a little bit bigger answer. The 400 volts for a 4.2, 4.3 segment and a 4.5, 4.7 segment, you have to combine it together. If at all you want an 800 volt, you will try it on a 4.7 meter, because once you put 400 volt, the electronics, the wiring harness, the controllers, the BMS, BDU, every part becomes expensive. It's really expensive. And that would not go augur well when we don't have the localized cell, localized motor, localized BMS, localized VCU, all of localized VCU we have it, but the remaining controllers we are yet to localize. So our idea is, while in the first 1 or 2 years, while you are importing all the BMS, charger, motor, and a cell, you stick to 400 volts and keep at a cost lower level and start localizing these components. And once you stabilize this for 5 to 6 years, then you bring in 800 volts. By the time you will move to the next orbit of 80 to 120 kilowatt hour battery pack, 1000 kilometers range, I would see 800 volts coming only in the 2028, 30 timeframe. Beyond that, I wouldn't see it now. It's very expensive.
Right. No, thanks for that perspective, Velusamy. Actually, we are running out of time. Time has gone very fast, but I think we have got some questions, and there's some technical questions which perhaps I would, like to pose. And I think maybe, Velusamy, you're best to answer this question from Rakesh Kumar is, do you see immersive cooling management finding a favor with OEMs? It's proven that immersive cooling has a much better capacity to arrest thermal runaway.
As I said, the NMC cells with very high energy densities, there is a technology, that technology is available. Right now, the safe bet is go with the current solution with the stop thermal propagation.
Right. And we'll take one last question, and that is from Prerna Goswami, who says, do you think there is a need to relook onto product liability regulations, since multiple tier products are linked when it comes to vehicle level? So you have to look at the liability too. Mr. Nagwanshi, you're in the US. I think you'd be best placed to answer this, country where these are big issues. So, just on product liability with EVs, your thoughts on that?
Yeah, it's a critical thing and really important. And ultimately the car manufacturers has to take a call and decide. And Derek, as a material supplier, we do our part with respect to generating the right data sets, conducting the right set of the testing, bringing the expertise in front of the customer to share this is the limit of the material, and let's see how best it can be utilized in the architecture of the car manufacturers. But yeah, in the United States, a really big issue, and if it can be standardized or made it more stringent, I'm sure it will help designing more safer electric vehicles.
Right. Well, thanks. I think on that note, we'll wrap up this session. I think it's been a very, very insightful session. I mean, as we said, we've had the whole supply chain represented here, right from the OEMs to the tier one component makers to the infra side, and of course even the material suppliers. Really, thanks. Thanks very much to each and every one of you for taking the time out. I think it's been very, very insightful, and I think a lot to learn, and really it's opened our eyes to a lot of new trends also that are emerging. Clearly, this is a very nascent segment, a lot of learning happening. Safety being one thing which has been rightfully given top priority, and clearly I think the steps taken to ensure that the products are safe, I think is going to give a lot of confidence to consumers as well. And of course, we look forward to great products in the future. This is the future. So with that, I'd like to say thanks very much again, and thank you. I'll hand it over now to Mayank. Thank you, everyone.
Thank you.
Thank you.
Thank you.
Thank you very much. Thank you to all the panelists. And thank you very much, Hormazd. Like you mentioned, it was a very all-encompassing discussion. We've included everybody, right, from OEMs, Mr. Velusamy, Mr. Singh from the component side, as well as Mr. Nahata from the infrastructure, charging infrastructure. We would now like to move to the next session, which is the technical presentation session. And I would now like to request Mr. Nagwanshi to please just stay back for this presentation. And it is going to be on the topic EV battery packs, the critical difference thermoplastics can make. I will give a quick introduction to Mr. Nagwanshi. He holds a master's degree in mechanical engineering from IIT Delhi and has been working with SABIC for more than 17 years in the US. He currently leads the global electrification team, which has made significant progress in optimization of battery packs and electrical systems with thermoplastic materials. Over to you, Mr. Nagwanshi, for your presentation.
Thank you, Mr. Mayank. Let me share my screen. Okay, great. Hope you can see my screen. So I will be presenting what critical difference thermoplastics can make when it comes to the EV battery pack. And we really had a very interactive panel discussion just a couple of minutes before that talks about the challenges for the safety, about the cost, reducing the complexities. So I'll share this journey, how thermoplastics can help the car manufacturers, battery suppliers, and the tier one partners. Mr. Mayank already talked about me. I work with SABIC. SABIC is a relatively young, but one of the fastest growing chemical company. Today, we are world's second largest chemical brand. We develop every year about 150 new products for changing market needs. As automotive industry is going through a seismic shift of electrification, we have some brand new offerings and a global dedicated team to serve you locally. So the whole world is moving towards the electric power. And particularly for the automotive, the EVs are kind of a seismic shift. It brings several advantages. Some of those we heard in the panel discussion. Beyond the CO2 emission reduction, the one and important thing is reduction in the complexity for the car manufacturers. For example, in ICE powertrain has about 1400 components versus an electrified powertrain has less than 200 components. So that's the kind of simplification the electric vehicles bring in. That's why several car manufacturers are investing in this space. About $560 billion have been already announced to enable electrification. But it brings several challenges from first is a mindset. From mechanical to electrical, electric vehicles are different. And then this brand new component battery poses some more challenges with respect to the safety, fire safety, electrical safety, plus the cost. Car manufacturers have been continuously looking for, hey, how can we reduce the lead time and the development cost at the same time reduce the cost of the car? In response to these challenges, SABIC recently announced a strategic initiative, Blue Hero. It's our commitment to enable electrification, and we are translating this commitment to the action through development and offering of an whole ecosystem, which includes very unique materials, flame retardant materials, ready to apply solutions, the solutions which are already validated that can help car manufacturers and the battery suppliers to reduce the lead time, as well as the expertise, the reach to our global experts to design this part with plastic more efficiently. So this is the whole ecosystem I have been talking about. The first and foremost is the materials, where we have been developing some very unique chemistries from the polypropylene, as well as the engineering thermoplastic materials like polycarbonate and polyesters. And these flame retardant materials bring a tremendous value with respect to stopping the thermal runaway. Then the batteries are becoming larger and larger. The question comes of how can you manufacture those parts? So we have been bringing all the know-how with large part with several manufacturing processes. Then joining these plastic part with the with other metallic components, steel and aluminum, and the fire polymer interaction. What actually happens when a flame interacts with a polymer? It's a complex science for which where our chief scientists, research fellows have been investigating, developing all the know-how, even developing mathematical models to help car manufacturers simulate these phenomena and look for using these materials for further optimization. Then application verification, where the geometry comes free with the plastics. You can make any shape with the injection molding or compression molding or with some limitation of a thermoforming. So if you design it right, it brings tremendous value. You can get a lot from the geometry. And the last one is that the whole solution development, where the value chain works together towards this big cause of clean air economy, collaborate and look for these new solutions together. So with that, I will jump to the solutions from the SABIC side that we have been offering to our customers. Our approach has been very simple. We start with the industry needs, and the three things that we have been quantified or we have concluded based on interaction with several customers across the globe, several car manufacturers. The first one is prevent the thermal runaway. Let's make it safer for fire safety. The second one is, can you reduce the weight and cost? So that's about reducing complexity. And the third one comes up, can we reduce the environmental impact? So looking at these industry trends, we have been developing the whole ecosystem of new materials, validated solutions, and bringing all the expertise together so that we can offer the true value to the car manufacturers and the battery suppliers with respect to reducing the weight of the battery pack, reducing the cost of the battery pack, enhancing the safety, whether it's a fire safety or electrical isolation or the crash worthiness, and reduce the environmental impact. So these are the solutions for a fire safety. The best thing is if the thermal runaway doesn't occur. But there are scenarios where this phenomena happens, and if we can prevent it at a cell level, that's the best solution. So that's where we have solutions for thermal barriers between cells. If not, then can we minimize the propagation between the modules? That's where our second set of solution comes up, which are module separators. So between these blue color boxes, the module separators. And if not, can we prevent the thermal runaway or contain the fire inside the module or inside the battery pack? With respect to the reducing weight and cost, plastic brings a tremendous advantage with respect to functional integration. One example is the battery tray. The whole tray, we have been engineering it with thermoplastics, and it brings the beauty of integrating the cooling channels right onto the tray. Similarly, for a battery cover with a steel, aluminum, SMCs, a thick thermal blanket is being used. So we're using a thermoplastic battery cover with a flame retardant material. You eliminate the thermal blanket. And from the battery modules, to make it not conductive with plastic, dielectric coatings can be eliminated. With respect to the environmental impact, some of these plastic processing methods are really less energy intensive and they emit less CO2 emissions versus the aluminum. Aluminum is a very high energy intensive process. So in that regard, designing these large parts with thermoplastics can bring reducing the environmental impact. So in the next few pages, I will talk about these solutions, starting with the fire safety to prevent thermal runaway. And I'll start with showing you a brief test. This is a plastic panel which is subjected to 1100 degrees centigrade temperature, very close to the thermal runaway temperature, for 5.5 minutes. This video is only the last 20 seconds of this test. But what happens when the heat comes in contact with the polymer, it starts forming a char, and over time, it becomes an intumescent layer. In the same test, if you conduct 1100 degrees centigrade for an aluminum sheet, there is a big hole in less than 1.5 minutes. Versus you can see with the charring phenomena, how the plastic is, the flame did not break through. The other unique property is the non-exposed side temperature. Plastics are not conductive to the heat. So the non-fire side, we have been able to limit the temperature to the less than 200 degrees centigrade. For a same test, the aluminum will be around 500 to 550 degrees centigrade temperature, and you need to have another thermal blanket if you're designing in a battery cover with aluminum. With this very encouraging results, we thought, okay, let's see what happens in an actual thermal runaway scenario. So I'll be sharing a test results from Underwriters Laboratories new test UL 2596. Let me run the video and then I will talk about it. So here are the two samples which has been tested. Left side, the standard plastic material. Right side is the SABIC solution. Nothing exciting happened on the right, which is a good thing. The material passed the test. The thermal runaway did not penetrate the plastic piece. This is the UL 2596 test, where it's a steel box. Inside that, there are 25 cylindrical cells, and then 2 cells are forced for a thermal runaway, which propagates to all 25 cylindrical cells. And this is one of the most stringent tests presently available today. The material which needs to be validated goes on a top refit and bolted here. And the pressures are about 256 kilopascal. So high pressures, all the ablatives are coming out, particles are coming out from the battery, heat, fire, everything is happening in this small test. You can see a standard material, how it fails versus the SABIC material, which is a flame retardant polypropylene resin with long glass fiber compound. You know, no one can believe a polypropylene can be made a flame retardant, polypropylene is generally like a wax. So that's where the chemistry comes into the picture, our experts comes into the picture, and we developed this brand new material that industry was demanding. Can you make a polypropylene that we can use in the battery pack? So yes, we have this material ready. This has been tested 5 times in this test, and every time we have passed this very stringent thermal runaway test. And I'm very excited to share that this resin family is already in production for globally the first use of plastics in a battery cover application for a PHEV battery with Honda in China. That meets very stringent fire safety requirements at the GB test standard. This battery cover is a 1.6 meter long part, which used to be a steel with thermal blanket. And we made it with together working with the Honda and our tier partner, a single piece injection molded solution that is 40% lighter. And also it brings a cost saving compared to the existing solution, steel and thermal blanket when we eliminate it together. This innovative solution also won the prestigious Edison Award earlier this year. Another example we'd like to share is the end plates. It's the cylindrical cells which are being used by the JLR, and the end plates which used to be the aluminum has been replaced with the SABIC's flame retardant polypropylene long glass fiber compound FR Staymax resin, which brings both the cost saving and the weight saving about 10%. So this was some of the solutions for a thermal runaway inside the modules or a pack, but let's take a look. Can we mitigate it between the cells? So this is the same test with the UL2596. This time we have made the cell partition walls, which are 2 millimeter thick, only 2 millimeter between the two cells. And we conducted the thermal runaway. And here are the results. The two cells which went for the thermal runaway, only those only those went for thermal runaway. All the neighboring cells has been protected with this 2 millimeter of cell barrier. We have also checked the voltage of all this remaining 23 cells, and all the cells have been working fine after the test, after that stringent test. So yes, these materials can be used to minimize the thermal runaway between the cells. This is an example for a cylindrical cells. And here is an example where we have been looking for a pouch cell batteries where the thermal barriers are generally flat plates. In this test, there are 3 cells which goes for a thermal runaway protected by 2 barriers, and the gray color are the neighboring cells where we are trying to protect these neighboring cells. In this test, the temperatures are about 1000 degrees centigrade. And when we do this test on a plastic piece and compare it with the incumbent solutions, which are generally the micas or the aerogel steel solutions, the backside temperature is really lower than the incumbent solution. So these materials can be also used for a thermal barrier between the cells, whether it's a cylindrical cells or it's the pouch or the prismatic cells. Now we'll talk about with respect to reducing weight and cost, what value thermoplastics can bring in. So next I will be playing a video about a conceptual design of a plastic intensive battery pack. All the color component here are made with thermoplastic. In this particular configuration, it's a pouch cell battery. But the battery enclosures or module housings, they are engineering are independent of the cell chemistry. So this is the first component we engineered with our flame retardant resins module housing. These sit on a battery tray. So that's the second component we engineered, which has integrated cooling channels right on the top surface of the tray. Plus it has a nail penetration features designed in the bottom. For the side crash, we have a plastic honeycomb structure on the frame. and a large top cover with a flame retardant polypropylene resin comes and sit on the top of it. So plastic can help with reducing number of components, improve safety, improve crash worthiness, reduce weight, and even increase the energy density. This looks like a very beautiful video, but it's a pretty much engineered design where we have been comparing it with the baseline aluminum. We tested this design for crash performance, all the side and frontal crash requirements. Stiffness performance from a modal analysis to twist analysis, structural performance from battery drop to the vehicle drop, stone impact, and other fire safety requirements. And this test, plastic intensive battery pack passed all the performance requirements. So yes, you can engineer this battery enclosures with plastics. Those are structural in nature, meet the structural performance requirement, impact performance requirement, and also these can be designed for the safer fire safety. So this is an example. We recently did a case study with the for Volkswagen ID4. We purchased a brand new vehicle here in the Detroit area, took the battery out. This is how the battery tray looks like, which is an aluminum intensive design. And then we engaged with Sandy Munro. He's one of a well-known industry critic, very globally known engineer. And his study concluded that engineering this component with plastic can help in reducing about 53% of the weight from the battery enclosure. The whole study is available in the YouTube. If you just search for a Munro Live, you can see how SABIC participated in this study, collaborating with the value chain partners and what value these plastics can bring in. And this is the prototype part, how a battery tray, which is engineered with plastic, looks like. Now we are taking this forward for the further validation with respect to all the structural impact and fire safety performance. Last, I'd like to touch upon very briefly about the environmental impact. And as I was mentioning, the plastic processing play a big role. These batteries are becoming larger and larger, anywhere from 1.8 meter long to 2.2 meter long. And you really require the advanced manufacturing technologies and the validations to make these parts, as well as the tier ones has to be ready as the car manufacturers start using plastic in these large applications. So we have been developing all the know-how with respect to injection molding this large part in a machines between 2,500 to 3,500 ton machines, even the other manufacturing methods like compression molding and thermoforming. The beauty is when we make these parts with plastic, compared to the aluminum, which is a highly energy intensive process, you reduce about 11% in the CO2 emissions, and you reduce about 13% in the energy uses. So the plastic brings advantage with respect to reducing the environmental impact. With that, I would like to conclude this presentation saying industry is really going through a seismic shift, and it's time to think differently, act differently with respect to the design, how the battery packs are engineered today, the materials which are being used today, the manufacturing processes which are used today. And it's not one person's job. The entire value chain has to collaborate, work together towards a bigger cause of a clean air economy, where thermoplastics can help with respect to weight saving, cost saving, enhancing the safety, and reducing the environmental impact. You can always learn more about SABIC's Blue Hero initiatives and our offerings in EV batteries and electrical solution space by searching SABIC Blue Hero, or go to the website sabic.com/en/Blue Hero. With that, I would like to really thank you for your time and your attention.
Thank you very much, Mr. Nagwanshi, for that lovely presentation. And we're getting so many questions from the audience. But before I go to the questions, I have a question, which I wanted to ask you. You mentioned about sustainability in your presentation, and it's a big topic now. Everybody is sort of focused on sustainability, ESG targets. So with these sort of alternate materials, so, our companies, how are they sort of, approaching the future when it comes to, the application of these materials in the overall attempt to reduce their carbon footprint? If you could just give your thoughts on that.
Absolutely. So the good thing about thermoplastics are they are recyclable. Not like the thermoset materials like SMCs and other non-ferrous materials or non-metallic material, which is being common in the battery enclosures. But these thermoplastics can be recycled. So the flame retardant resins that I have been talking about, we have broken those parts, remelted it, made a part again, similar fire performance. Broke it again, remelted it, made a part again, up to 4 times. So yes, these materials can be recycled. The difficulty is having the closed loop structure. Today's recycling technologies are just extract the critical raw materials, the expensive materials, metals. But as these technologies develop, the value chain is ready. Thermoplastics can bring tremendous value with respect to making the whole battery pack recyclable.
Sure. And also from a cost perspective, Mr. Nagwanshi, so, when you're talking about such levels of, recyclability, so does it also come at a cost when you compare it to conventional metals or other materials?
It really depends upon the scale of operation. So if the scale is available, the value chain is ready, then the cost can be competitive for the recycled materials. From the SABIC side, we have a whole new portfolio under the True Circle initiative, where we have the both different kind of recycling materials, from mechanical recycle to the chemical recycle materials, and even the bio-based materials in our portfolio to help our customers. The initial cost could be a little high, but as these solutions are scaled up and the industry start adopting the recyclable materials, have tested the performance of these materials as good as the virgin materials, then with all the functional integration that plastic can bring in, all the geometries you can design, you need not to weld two metal plates to make a channel. You can just mold it. So that's where the value comes in.
Sure. I'll now switch to taking questions from the audience. And the first question is related to your presentation. So what is the minimum thickness possible for the thermal barrier material? I think this must be in some of one of your slides in the presentation.
Correct. For the cell-to-cell propagation, we have been looking at around 2 millimeter of the thickness. Those are the commonly used material, as I was sharing, for a cylindrical cell batteries, 2 millimeter, even for a pouch cell batteries, depending upon the architecture, 2 millimeter is the minimum thickness. Ideal thickness for the battery enclosures and the module component is about 4 millimeters. So that's a thickness we have been looking.
Sure. I go to the next question, which is from Mr. Taha Sheikh. Sorry. Is it recyclable polypropylene?
Yes, these materials presently are not based on the recycle stream, but it's a flame retardant polypropylene resin with glass fibers. So it definitely a recycled polypropylene stream can be used to make these materials with the recycled content.
Sure. And another related question is from Mr. Akhil Baluja, how the batteries would be discarded or will they be recycled?
It has to be recycled. There will be so many electric vehicles coming in the future, and there's so much of good materials that goes into the battery. It has to be recycled, and there has been several initiatives across the globe about making the value chain ready and making the technologies ready so that these recycling can happen and can be done at a lower cost.
Sure. So I think with that, we'll bring this session to a close. Thank you very much, Mr. Nagwanshi, for your presentation and for taking all the questions from the audience. I think people really enjoyed it, and they're finding value in this conversation with you, getting to know about your products and the materials that you're offering for future EVs. So I would just request you, if you could just type in your email ID in the chat box, so that if anyone wants to get in touch, they can reach out to you in the future. And with that, I would like to thank everyone who has joined in for this event, the 2 days of Autocar Professional EV Forum for passenger vehicles. We really appreciate your time and your joining. And I would also like to thank our sponsors. The event has been powered by Ascend Performance Materials and Covestro. materials partner SABIC, associate partners Arkema and ATS. Mr. Nagwanshi, thank you once again. And with that, we would like to close this event, and we hope to see you soon with another event. I've also mentioned the YouTube link in the chat box, so you can find the recording of the 2 days on this YouTube link, and you can access all the presentations as well as the panel discussions by reaching out on the link, and you can watch the videos in a recorded format. So thank you once again. We hope to see you soon with another event. Thank you very much. Goodbye.
Thank you very much. Good day.